Okay, so we'll start our discussion of the chain rule, really looking at the conceptual basis behind it and why we need it, really. So on the front page, we have this idea that y equals the number of calories burned. So we see this expression dy du, and u is the number of minutes spent running. So then by definition, dy du must be calories burned per minute. Now, meanwhile, we have this expression du dx. And we already know u is number of minutes, but now we have this variable x, which is number of miles run. So by definition, this must mean that du dx is minutes per mile. So you might be able to see where this is going to take us, possibly, and that is that when we put the two together and we say, let's do dy du times du dx, right? We have units here that are canceling out, so in other words, minutes, and that leaves us with dy dx represented as calories burned per mile. And that, in essence, is the chain rule. So now the question is, how do I apply that when I have an actual function in front of me? So let's take a look at an example. Let's suppose we let h of x equal f of g of x. So we've seen this before. It's called composition of functions. Let's say in this case it's equal to the square root of x squared plus 1. So what we want to do in a case like this is we actually want to take a minute and recognize what we have here. So we do have two different functions. We have what we call an outside function and we have an inside function. So let's let the outside function be f of x and the inside function be g of x. So the inside function is really x squared plus 1, no radical, nothing like that, whereas the outside function is simply the square root of x, or we can even look at it as x to the 1/2. Because if I were to take this inside function and place it in f of x for x, I would actually achieve the function that they've given me. So that, in essence, is where this dy du and du dx concept comes from. So another way we state the chain rule is we say, well, if we have a composition or a composed function identified, then the chain rule says you're going to take the derivative of the outside function, maintaining the inside, and then you're going to multiply that times the derivative of the inside. So this right here is our chain rule. So now how does that look with this particular example that we're dealing with here? Well, the derivative of x to the 1/2, so we'll call this h prime, right, will be 1/2, and your tendency early on is going to be to say x to the negative 1/2. But really it's not x that's inside there. What it really is that inside function x squared plus 1. And then we're going to be multiplying that times the derivative of g of x, the inside function, and that's 2x. So when all is said and done, if I wanted to, I could simplify a little bit, right? This 2 and that 2 could cancel, and I could actually say that my final derivative was something like this. Okay, obviously this is just one example, so we need to look at a couple other situations, scenarios, so we get a little bit more comfortable with what we're looking for. So let's take a look at another one. Okay, in your notes we have example 1 here, and that is f of x is equal to 3x minus 2x squared, all raised to the third power. All right, so again, keeping with the idea here of an outside and an inside, let's use O for outside this time. And let's use I for inside. So just changing it up a little bit. I mean, it's basically f of x and g of x, that's all. So the inside function, again, is this polynomial that's being raised to the third power. and the outside function is simply just x to the third power. Again, think about this, right? If I were to take this and replace it in here, I would get right back to where I started, which was the original function. So if we apply the chain rule now, it says, let's get the derivative of the outside, so 3x squared. So we'll say f prime of x will equal 3x squared. But for me, that means that this polynomial has to remain, right? Then times the derivative of that inside function, so 3 minus 4x. Now here you're done. I mean, there's really not any reason to go further. I mean, I suppose you could distribute the 3 in there, but I don't really see where it would get you. So again, just another example of a function being raised to a power, probably the most common function at this point, where the chain rule would be necessary. Okay, let's look at another example. Let's look at example 2, right? So now that we have g of x equals cosine squared of x, and at first glance, you say, well, this doesn't really look like the ones we've done, and that might be true, but maybe if we rewrite it, cosine of x quantity squared, now it looks again like that idea of function, right, here we go, being raised to a power, where the outside function, we'll call it f, right, that would be x squared, and the inside function, let's call it the h this time, would be cosine of x. So derivative of the outside, 2x, so in this case, that's really 2 times cosine, reduce the power, so now we're down to 1, right? And then multiply by the derivative of cosine, which is negative sine x. Now, again, I'm fine with this right here. It actually wouldn't be outlandish for somebody to write negative 2 sine of x, cosine of x. That's actually a little bit more standard to put sine before cosine, but it's not a necessity. Okay, so again, the first 3 examples we've played with here are function to a power. Let's look at what happens when we maybe remove the power as one of our composite functions. Okay, let's look at example 6. So we're given f of x equals cosecant of 4x squared minus 3x. Okay, so again, try and identify inside and outside, right? So the outside function is going to be simply the trig function, and the inside function is going to be that polynomial right there. So this is new for us because up until now we've only seen a function being raised to a power, and that's kind of how we compose two things. Here we have the angle of a trig function. That's our inside function. Okay, so let's kind of split them up here. One of the functions we have is cosecant of x. The other one is 4x squared minus 3x. So the derivative of the outside, so the derivative of cosecant is negative cosecant x cotangent x times the derivative of this inside piece, so 8x minus 3. Now you notice I didn't put anything in parentheses yet because I wanted to make sure we understood that even though the derivative of cosecant is negative cosecant cotangent, I still have to maintain that original inner function here. And then I'm done. So something new here where the angle winds up being the inside function. Let's look at one more. We're going to go to example 8 here. Right, y equals e to the x squared over 4. So now we're back to that power idea, but it's a little different because we have e, right? So what if we let f of x equal e to the x, and let's let g of x equal 1/4 x squared. Just writing a little different there, right? So the derivative of the outside is itself so dy dx equals e to the x times the derivative of the inside, which should be bring the 2 down, so 2/4 or 1/2 x. And remember, what would have been up here? It's x squared over 4. So it's e to the x squared over 4 repeated, right? Times the derivative of the exponent, which is 1/2 x. So again, these are just some examples to kind of get us started here. We'll obviously talk about a lot more in class. Try the other ones. Let me give you some of the answers to those so you have them. Okay, we did not do example 3. And we're going to do that in class. There's a lot going on there because there's a product and a quotient rule. But if you want, you can try example 4, and you should wind up with -3 sine 3x. You can try example 5, and that one you should wind up with -2 over 3x minus 5 cubed. And if you want to go all the way down to 7, -5 sine of 5x secant squared of cosine of 5x would be your answer there. So I hope this video at least got you started a little bit with the chain rule, and we will have a lot more to talk about in class.